Alright, so I didn't get a chance to go over the review sheet in class. We ran out of time, so I want to briefly go through the review sheet now. So for the final exam, it will cover mostly chapters 8 and 9, although I dipped a little bit into chapter 10. So it'll cover the chapters on um, experimental design and a little bit on quasi-experimental design. So I differentiated types of designs by calling them, some of them weak and some of them strong experimental designs. Basically, the strength of an experimental design has to do with how well it rules out confounds or rival hypotheses, or in other words, alternative explanations. Another way to put that is it has strong internal validity. So internal validity is the confidence with which we can rule out alternative explanations for any findings that we have in an experiment. Now remember, an experiment, the purpose of an experiment is usually to determine the effect of some variable. We'll call it the independent variable, or you can think of it as like a treatment variable or an intervention variable. So if we were trying to see, let's say, what was the effect of some new treatment for social anxiety, in order to design a good experiment, we would need to have a good, what I'll call counterfactual. The counterfactual would be like, what would happen if we didn't deliver this treatment? So let's say we developed our new treatment, we administered that treatment to some people who have social anxiety disorder, and we found that their social anxiety disorder went down. It doesn't necessarily mean that it was the treatment that led to the decline in social anxiety, because we don't have a good counterfactual. So to have a good counterfactual, we need to have a condition, really, where we can compare it to what would have happened if the individuals would not have received the treatment at all. Now obviously we can't clone those individuals at that point and run the experiment on randomly on the cloned and uncloned individuals, having half of them get treatment and half of them not get the treatment. So we have to find some other means to strengthen internal validity by having a good comparison or control group. So we'll start off with weak experimental designs. Weak experimental designs are basically the ones that do not allow us to make strong causal arguments, mostly because they don't involve random assignment to conditions, or in some cases they don't even have a control or comparison group. So the one group post-test only design is basically, it is kind of what it sounds like. There is only one group, let's call it the treatment group, and there is only a post-test measure. So if we wanted to test the effects of our treatment for social anxiety on social anxiety, and we only put people in the treatment condition, that would be a one group post-test only design. So let's say we have some new treatment we've devised. We'll let this beautiful square here represent that treatment. So here is the treatment, and then we measure the dependent variable, which will be social anxiety. That would be a one group post-test only design. It's hardly an experiment, because let's say we find that after the treatment levels of social anxiety are moderate or low or weak or strong. We have nothing whatsoever to compare that to, so we don't know if the treatment was effective at all. So that's kind of, if you want to call that an experiment, it is probably the weakest sort of experiment that one could design. It's not to say that those sorts of studies aren't run and that they can't provide some useful information, but they provide rather minimal information. All right. A little bit better would be a one-group pre-test post-test design. So a one-group pre-test post-test design would really involve the treatment, but we measure social anxiety pre-test, before, and post-test after. So it allows us to see, is there a change? So we can see, hopefully, we would hope that after treatment, levels of social anxiety would go down. But just because they go down does not mean that it's the treatment itself that causes the social anxiety to decline. So although it gives stronger evidence, certainly, than the one group post-test only design, the one group pre-test post-test design allows us to see if the levels of the dependent variable have changed from before until after treatment, but they do not, it does not allow us to say with any great certainty that it was the treatment itself that caused the change. So it could have been some regression to the mean, where let's say we picked people to begin with who had very strong levels of social anxiety that upon a second measure would have gone down anyway. It could have been that people became more comfortable in the testing environment or the environment in which the scale was administered, so that pre-test was rather high and post-test was rather low, and the treatment really had no effect. Or it could be that the treatment, if we do find a decline in social anxiety, it could be that the treatment did in fact have an effect. So it's difficult to know if you see a change from pre-test to post-test in a one group design. Is difficult to know if it was the variable or the treatment or intervention you're attempting to assess, or if it was some change due to another extraneous variable or situation. Alright. The post-test only with non-equivalent control group design is kind of a mouthful, but it's basically a quasi-experiment with only a post-test. So let's say we had a treatment group and we'll stick with the example of some treatment for social anxiety, and we have a comparison group, let's say a no treatment comparison group, so these people don't get the treatment. And let's say the treatment group we got because they were able to have insurance that covered this new experimental treatment. Their insurance was willing to cover it, or they had the funds to cover it themselves. And the no treatment group, or even it could even be an alternative treatment group, maybe they're not getting no treatment, but they're getting an alternative treatment. They were people who, for whatever reason, didn't have the funds to cover the new experimental treatment. Now this would not be like a true experiment in the sense of a randomized experiment, because we might expect the people who are coming into the experiment or the study, they may differ in pre-existing ways. So when we assess the dependent variable social anxiety after the treatment or no treatment is administered, we won't really know, is it because of the treatment? So let's say the people in the treatment group have lower social anxiety than the people in the no treatment group. If that's the case, we won't really be able to say with great certainty that it's the treatment that led to lower social anxiety, because there may have been pre-existing differences in the first place. So one design element you can add here to, assuming you can't randomly assign people to conditions, a design element you could add here is you could add a pre-test post-test. So you could have a pre-test post-test with non-equivalent control group design, where you measure social anxiety at the pre-test and then again at the post-test. So it would allow us to see, okay, are there pre-existing differences between the treatment group and the no treatment group to begin with, right? So if there aren't any pre-existing differences to begin with, then you're probably in pretty good shape, even though you haven't used random assignment here. But of course, ideally we would use random assignment. So the strong experimental designs that we're going to cover now use random assignment. Random assignment is simply putting people into the conditions of the experiment at random. So random chance decides which experimental condition or which level of the independent variable a person is assigned to. And when that occurs by random chance, then you would be relatively confident that the groups will be similar, so that there will not be pre-existing differences before the treatment is administered. Which is really what we're trying to rule out, is that things that people bring into the study, their level of intelligence, their personality, their income, their socioeconomic status, their mood, so on and so forth. We could name thousands of things. If we use random assignment, we can be relatively confident that the levels of those two variables, assuming we have reasonably large samples in each group, the level of those two levels of those variables will be probabilistically similar across the two conditions. It doesn't mean they're going to be identical. It doesn't mean that there can't be some variables that differ across the two conditions, because it is random, but it means that those two groups will be, or however many groups are in the experiment, will be probabilistically similar, or they'll be very likely to be similar, so we can rule out things that the participants might bring into the study as potential confounding variables. So in a post-test only control group design, that would be when we have, let's say, our treatment and control condition. So we have treatment and we have control, and people show up to the experiment. They are randomly assigned to be in either the treatment or the control condition, but it's random, and the outcome is measured after the treatment is administered. But because people are assigned to the groups at random, it means that the groups beforehand will be probabilistically similar. So we can rule out pre-existing differences or selection biases. Whereas in the previous example, with the non-equivalent control groups design, we could not rule out pre-existing differences or selection biases because people were not randomly assigned to the conditions. So that is the post-test only control group design, kind of the classical example of what might be called a randomized controlled experiment. Now, of course, in the context of this design, there's other variables that the researcher would want to control that aren't participant-related variables. So, for instance, perhaps the nature of the therapy, how the therapy is administered, how participants in both the treatment and control condition are recruited for the study, how they're asked to complete the dependent variables. So in an experiment, the goal is to isolate and control as many extraneous variables as possible so that we can have high internal validity for the study. In other words, so that we can have confidence that it is our independent variable that's leading to any difference in the dependent variable, and it's not any of those extraneous variables. An additional design element which would make an experiment a bit stronger is a pre-test, post-test control group design. So a pre-test, post-test control group design is similar to the design we just discussed, except for now it has a pre-test. So the great advantage of a pretest, there's two major advantages of a pretest. One is it allows you to assess change. So you can see, okay, does social anxiety decline in the treatment group from pretest to post-test? Does social anxiety perhaps stay the same, go up, or at least not decline as much in the control group from pretest and post-test? So a successful experiment here would be when there is a greater decline of social anxiety from pretest to post-test in the treatment group as compared to the control group. So another advantage, so pretest, one advantage is you can assess change. If you have a pretest and a post-test, it essentially becomes a longitudinal study where you can assess change. But another advantage is you can make sure your randomization works. So if you randomize people into the two conditions, and you can check by the pretest scores before you even administer the treatment to make sure your random assignment to conditions was successful, because it is a random process. So it is possible that you randomly assign people to conditions, and by some random bad luck, people in the treatment group had much higher levels of social anxiety to begin with than people in the control group. So if you saw that, you could catch it and perhaps randomize people to conditions again, and then hopefully then it would even out. But the random assignment, of course, is not perfect, but it is a good way of making sure that people are reasonably similar before the experiment starts. So pretest helps by allowing you to assess change and also by allowing you to assess to make sure that randomization of the people to conditions was successful to begin with. All right. A factorial design is one where there are multiple independent variables. So let's say we wanted to look at the effect of treatment and condition, treatment and control rather. Treatment and control, we're interested in that, but we want to see, does it differ for, let's say, let's just do something simple, male versus female clients. So this would be an example of what we could call a factorial design. So there are multiple independent variables here. This specifically would be called a 2x2 factorial design. 2x2. So there's two levels of the condition variable, which is treatment or control, and there's two levels of the gender variable, which is male versus female. Now we should note that actually the treatment and control variable, if we have random assignment, that would be an experimental variable. And the gender variable, male versus female, in this context, it is not an experimental variable because you can't randomly assign people to be a certain gender, right? So this would kind of be a mixture in this example of a experiment and a quasi-experiment kind of smashed together. Alright, so in any case, that would be a kind of simple 2x2 factorial design. Now in a factorial design we can have main effects. Main effects are the differences, usually if we're talking about mean differences, the differences in the means across one independent variable kind of ignoring or collapsing across the other independent variable. So let's say we had a main effect for treatment here. It would probably mean that the treatment condition led to lower social anxiety, right? The treatment condition led to lower social anxiety than the control condition, kind of ignoring gender. Or if we had a main effect for gender here, we would see that let's say the males had lower social anxiety than the females, right? So the males had let's say lower social anxiety than the females, ignoring treatment, right? So that would be an example of a main effect for gender. A main effect for treatment would be a difference between the two treatment conditions, or a main effect for condition would be a difference between the treatment and control conditions. Perhaps more interestingly, in a factorial design, usually researchers are looking for this sort of thing, is an interaction effect. So an interaction effect is when the effect of one independent variable, let's just keep it simple at a two-way interaction. An interaction is when the effect of one independent variable on the dependent variable. So we've got the effect of one independent variable on the dependent variable depends or is influenced by the level of another independent variable. So in this example, let's say we have a difference between treatment and control such that treatment leads to lower social anxiety than control, but let's say the treatment is more effective for females than for males. So if the difference between treatment and control is greater for females than it is for males, then that would be a statistical interaction, a two-way interaction in this factorial design. So basically, for an interaction effect, we're basically looking at when the effect of an independent variable on the dependent variable is different at different levels of the other independent variable. So, what is the purpose of a control group? Well, the main purpose of the control group is to provide the ability to see what would happen if we hadn't administered this treatment or if we hadn't administered this intervention. So the control group ideally is as similar as possible, is treated identically to the treatment group with the exception of whatever critical element of the treatment whatever the critical element of the treatment is thought to be. So that's the main purpose of the control group, is to provide basically a counterfactual comparison for us to be able to see what would happen if we hadn't administered this treatment at all. Alright. As we've already discussed, random assignment to conditions is basically when you put people into conditions by a random process so that the conditions will not be different at the outset of the experiment, so that you can rule out pre-existing differences as being the cause of any differences you might find in your dependent variable after you've administered the treatment. So random assignment to conditions, again, simply allocating people or cases to the different conditions of an experiment at random so that you can rule out pre-existing differences between the groups as being a rival hypothesis or alternative explanation for your results. We also talked about the conditions for causal claims. So in order to make a causal claim, there's generally three conditions that need to be met. The first is the relationship condition, and that is, if you want to make a causal claim, you have to show that your presumed causal variable is related to the presumed outcome variable. So if they're not related, let's say you think X causes Y, but you can't even prove that X is related to Y, you're going to have a hard time with making a causal claim. You're not going to really be able to move forward from there. So first you have to show that the two variables are related. If you think one variable causes the other, you need to be able to demonstrate that they're related. But, as you know, just because they are related, it does not mean that there is a causal relationship. So after you've established, or while you've established a relationship or correlation between the variables, you also need to establish temporal order. Temporal order basically means that the changes in the presumed causal variable, we'll call it X, must occur before the associated changes in the presumed outcome variable or dependent variable. We'll call that variable Y. So changes in X must precede, the associated changes in X must precede changes in Y. In other words, basically what we're saying here is that cause must come before its effect, right? Cause comes before effect. Finally, and probably the hardest condition to make causal claims, is that you must rule out alternative explanations. So this is why in an experiment, it's probably the best way to address this condition, and that is to rule out alternative explanations. So in order to do this, we would control, to the extent possible, extraneous variables so that we can be sure that they don't differ between our conditions in the experiment, and we would also employ random assignment to conditions so that we can rule out pre-existing differences between the groups as alternative explanations. They can still creep in, of course, in an experiment, but the best way to address all of these causal claims is in an experiment, because if you run an experiment and you find a difference in the means, let's say comparing your treatment and your control group, you've already established a relationship condition, and you've already established a temporal order condition because you manipulated your IV before you measured the differences in your DV, your dependent variable. And then if you've done the experiment properly, where you've controlled extraneous variables and randomly assigned people to conditions, then you're also able to rule out alternative explanations. So if you run a well-designed experiment, you'll meet these conditions for causal claims, and you will have relatively high internal validity for your study. Right. We also talked about within subject variables versus between subject variables. So within subject variables are ones in an experiment where people are going to take part in each condition. So let's say there's two conditions in the experiment. We'll just call them condition A and condition B. People who take part in that experiment will be in both condition A and condition B. Now, the order may be randomly assigned, so that some people show up to the experiment, they get B first and then A. Other people show up to the experiment and they get A first and then B. The main advantage to doing an experiment like that is you typically need much fewer people to get enough power to detect any differences that might be there. So people basically will serve as their own control group or comparison group, within subjects' design, which is often very desirable, especially if you're an experimenter and you don't want to run a large number of participants in your experiment. The downside, and there's several downsides, but they basically boil down to once you've given someone a treatment, it can have an effect on the subsequent condition that they're in, right? So this can only work in experiments where there's not going to be a lot of carryover effects or order effects in the experiment. So once you're in condition A, that might influence how you respond to condition B, or once you're in condition B, that might influence how you're going to respond to condition A. So let's say you were doing an experiment and you wanted to see how caffeine consumption affects, let's say, recall of let's say, learning some words. Now, if you had people in the caffeine condition and then you subsequently put them in the non-caffeine condition, it wouldn't make a lot of sense because the effects of the caffeine would still be affecting them unless you waited a long amount of time in between the two conditions. So in many studies, it may be not feasible to do it within subjects design, but when it is feasible, when there's not a lot of concern about carryover or order effects, or when being in a within subject design doesn't invalidate the study by making it completely obvious what's being studied, and that in turn might influence people's behaviors. When those things are not going to occur. So in many cognitive experiments, you'll see that they'll use within subjects designs because it's not really necessary to have a cover story to disguise the true nature of the study, and there's not a really strong problem with order and carryover effects. You'll see that cognitive researchers will often do a within subjects experiment. Between subjects experiments, or when it's kind of how we've been talking about it all along in this course, as if all experiments are between subjects. Between subjects experiments are when participants are in one level of the independent variable, but not another. So within, participants take part in multiple levels of the independent variable. Between, a given participant will only be in one level of the independent variable. So in other words, with between subjects designs, the groups are independent. With within subjects designs, people are in each group. Alright, internal validity is kind of what this experimentation is all about, and that's really the strength with which you can make causal inferences as the result of your experiment. So if you're able to rule out extraneous variables, if you're able to rule out confounds, if you're able to say that it likely was your independent variable or the manipulation of your independent variable that caused a difference in your dependent variable, then you have a study with strong internal validity. So well-designed experiments, that's basically what they do. They have strong internal validity. They allow the researcher to make a strong causal argument. Correlational research, on the other hand, would be low in internal validity because it does not allow researchers to make strong causal arguments in most situations. All right, an extraneous variable is just another variable that might influence your dependent variable. So in an experiment, ideally, we control and limit the influence of extraneous variables on the dependent variable so that we can isolate the effect of the independent variable on the dependent variable. Now, a confound is a particularly evil type of extraneous variable. A confound is an extraneous variable that varies systematically with your independent variable in such a way so that you don't know if it's your independent variable that caused the difference or if it was your confound, or the confound that caused the difference. So going back to our example from before, let's say that we were randomly assigning people to the treatment condition and a waiting list control condition, and then after 2 weeks we assessed their level of social anxiety, and lo and behold, we found that people in the control condition had lower levels of social anxiety than people in people in the treatment condition had lower levels of social anxiety than people in the control condition. Well, that would be all well and good, but let's say we also found out that the people in the treatment condition completed the measure of social anxiety at the psychologist's office, whereas people in the control condition completed it online at home. Now we've introduced a confound. The confound being that the people in the treatment condition always completed the assessment of social anxiety in the psychologist's office, and probably having the psychologist nearby affected how they responded to the social anxiety measure, especially after they've been receiving treatment from the psychologist. The people in the control group, they did it at home. So that varies systematically. That's a difference between the two conditions. That varies systematically with the independent variable treatment versus control, so that they're not really being treated similarly anymore. And we wouldn't be able to rule out if it was the treatment that caused the difference in social anxiety scores after the intervention, or if it was just a different method of administering the social anxiety measure. So as you can see, a confound is a particularly troubling aspect of an experiment that can just kind of ruin the results of an entire experiment by perhaps not even intentionally introducing some systematic difference between the conditions in the experiment. Alright, so the threats to internal validity, sometimes they're also just called confounds. There's many of them, as you can review in the textbook, and they've been given various names. I'm just going to go over a few of them. One is maturation. So that's if you find a difference between your conditions and you're not sure if that difference is just due to some natural change over time, or if it's due to the experiment or the intervention itself. Now, that really shouldn't be a problem if you use random assignment, because if you use random assignment, you're going to assume that there's going to be similar amounts of maturation across the two conditions. So this is really a major concern for single group experiments, and potentially for quasi-experimental designs where you might have differential rates of maturation across the two groups. But for the most part, if you use random assignment, you can usually rule out maturation as a threat to internal validity. Testing might occur when you see changes due to the way that the measure was administered, or just simply, I should say, simply having experienced the measure multiple times. So let's say we were designing an experiment where we wanted to see if we could improve people's standardized test scores. And so they took a standardized test, let's say the ACT, they took the ACT at time 1, we gave them some intervention to help improve their ACT scores, and they took the ACT at time 2 and they did significantly better. We would probably want to say that it was our intervention that led to the increase in ACT scores. The problem would be just taking the ACT twice might get you more familiarity with the test, and more familiarity with the testing situation might reduce test anxiety, so on and so forth. So we wouldn't have great confidence that it was our intervention. It may have just been people getting used to the test itself that led to the higher test scores. So ideally we'd have to have a comparison or a control group, which would help us to rule out testing as a threat to internal validity. Mortality threat to internal validity occurs when we have differential attrition or dropout or non-completion of the dependent measures across groups, or just in general. So let's say if we were implementing a a intervention to try to help people quit smoking. And let's say we didn't run a good experiment, we just had one group pre-test, post-test. We get a bunch of smokers, we enroll them in the study, we do the intervention, and then we record did they quit smoking, let's say 6 weeks later. Half the people drop out of the study. Of the people who remain in the study, let's say half of those quit smoking. So we can say, wow, our intervention's pretty effective. Half of the people we were able to measure quit smoking. Well, the problem is that we don't know what happened to the people who dropped out of the study. So most likely they did not quit smoking. We don't know that for sure, but most likely they did not. So having them drop out makes our intervention look a lot more effective than it actually is. So when people drop out of a study, it's ideal that they don't, but it's just going to happen sometimes, especially for longer longitudinal studies. When people drop out of the study, if you have random assignment to conditions, you just kind of cross your fingers and hope that they dropped out at similar rates, let's say in the treatment as compared to the control group. If they drop out in similar rates in the treatment and the control group, it's kind of less of an issue. But if you have more people dropping out of the treatment group than the control group, if you have differential attrition or dropout across groups, then it becomes more of a problem and a threat to your confidence in the results of your experiment. Regression threat to internal validity occurs when you select people who score either very highly or very low on a measure. So if you deliberately select people from the get-go that score very highly or very low on a measure, you're going to potentially run into this issue of regression to the mean. And that's basically, let's say if you measured people's social anxiety and let's say you found a bunch of people who scored very high on social anxiety. If you waited, let's say, a day or a week or whatever and measured them again, their levels are probably just going to go down. Mostly because that's the only place they can go. They can't go up. If they're towards the highest end of the scale, they're more likely to go down than up. So if you deliberately pick people who scored very high on social anxiety, you administered your intervention or treatment, and then you measured it again, you might see that social anxiety went down. It doesn't mean it went down because of your intervention. So that's why you would need a control group. You got a control group, you can randomly assign people to the conditions, and you can see, okay, well, it did go down in the control group because of regression to the mean, but maybe it went down even more in the treatment group, so you can rule out regression to the mean as being a major threat to internal validity. All right, so these threats to internal validity, maturation, testing, mortality, and regression, they're primary threats for single group experiments, which are generally just bad ideas to conduct in the first place. Because with single group experiments, you have all these threats to internal validity that can pop up. Now, it is possible for some of these to rear their head in a more proper randomized experiment or in an experiment that involves random assignment to conditions, but that generally that can be termed a selection bias. So that can occur when people in one group are different from people in another group for whatever reason. So if you have people in one group who are maturing at a faster rate than people in another group in your experiment, then you can have a maturation threat that it's basically an interaction between maturation and the experimental condition. So these things can occur in a experiment with random assignment to conditions, but in that case it's usually because either random assignment was done poorly or just by chance it didn't work out very well, so that there were pre-existing differences between the groups when in fact there shouldn't have been, or due to random assignment, or if people are treated differently in the two conditions. So if a confound is introduced, then that could also lead to differences between the two conditions, which would weaken the internal validity of the design. So although of course threats to internal validity are a concern in randomized experiments. They're just less likely to be an issue if the randomization is done properly and the experimenter doesn't introduce confounds into the experiment. Alright, so if you have any questions or concerns about this information, please be in touch. Email me as soon, because we're kind of running out of time until the final. But let me know as you review this if any issues pop up. Alright, goodbye.